Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. I'm laughing too much over here. The light's on.
Oh my gosh.
The light's on, Chris.
Jesse. What are you doing here? So every once in a while, when you're in charge of a script, I don't know what happens to you. You go down, you're like the black hole of, and today you're the black hole of all things Garnet. This was, I picture you sitting there with your keyboard in front of you and you're just happily, almost giddy, like typing this script out. And you're giggling and you're laughing. Like, I don't know what the heck
Do you imagine me
on.
like the cartoon character, like big typing with the lifting your hands up, and typing, big typing?
I do. Yeah, you're like prancing with your fingertips.
Wile E. Coyote kind of typing
you're
going
high
on.
stepping. What is this? Jesse, oh my gosh. A little over the top. I have my work cut out for me. You're not the good doctor today. You are not Dr. Ryming.
No, I'm not.
You're full on professor. Like
okay, good.
Head of the department.
I'll take it. Hey, there we go. I'm getting promoted. This is great. On that note, Chris, I have a question for you. And I'm asking you because I really want to talk about me a little bit, but I want you to go first. Do you guys do teaching evaluations? I mean, do students do teaching evaluations every year for you in some way, shape, or form?
That's up to the individual teacher to do that. Yes.
So like you're not required to have
student evals of us?
Yeah, in some way, shape, or form.
No.
Oh, really?
No.
Oh, that's interesting. No. Okay. Do you choose to get student evaluations or not?
I did for the bulk of my career. I don't do it anymore.
So you said you hit the button that said, I don't want to hear any more student opinions about me.
Okay, that's a really interesting thing because I have some thoughts on this.
Okay.
I felt like it got to be a little self-serving. I don't know if that makes sense.
Oh, yeah, it totally makes sense. Actually, it totally makes sense because of why it came to my mind, because I was putting my teaching so I'm putting my tenure package in this fall. So I was like going through, you got to do all the stuff, put all my things, everything I've done, students supervised, mentored, class reviews. So I was like digging deep into, we have, I forget what they're called, SRTs or something like that, but student evaluations that you ask the students to do. They're not required to do it, but you have to ask them. And then these get aggregated. There's a bunch of things that they give you a score on how good your class was organized, how good of a teacher or whatever. But there's a couple, I got into the comments section from the last couple of years. And one of them really stood out to me for exactly the same reasons you're implying. It said, whatever Penn State is paying Professor Remick, it's not enough, which I wanted to just copy paste and send up the chain, as like, promote me. Good. The students tell me I need to be paid more. I mean, there was some not so positive ones as well in there, but the positive ones stood out to me. So
yeah.
Anyway.
And I felt like they were starting to affect me in a negative way.
Okay.
Where I didn't want to become a different person because I wanted that.
You don't want to like change how you teach and how you do things in order to cater to like positive comments from students and things like that, or
yeah. And the vast majority of them were positive, and I guess like I was afraid of becoming addicted to that.
Yeah. For sure.
I think that's the way I want to say it, I guess.
Yeah. I mean, I'm sure it's like social media. You post things and get a bunch of likes, and it feels good. But
that's right.
You don't want to be addicted to that.
That's right.
Yeah, I totally get that. I mean, we're required to do it, and I generally ignore him. I've never been on Rate My Professor and looked at myself or something, but I was kind of forced to.
Is
in a
that
way,
still
for
a thing?
tenure.
I don't think it's a thing anymore, is it?
Apparently, there was a discussion about one of my colleagues about how many chili peppers they had. So apparently, it does still exist. It's not as common as it probably was when I was in college, but yes, you can still get chili peppers apparently.
All right.
Yeah.
All right.
So anyway, it's out there.
Okay, so you're going through the process.
Yeah, I wanted to know what your, like, if you guys had to do them, like what your student evaluation kind of requirements were. So anyway, I wonder what the listener evaluations will be of my way too deep, way too dark Garnet script here in this episode.
Well, it's actually going to fall more upon me than anything else, because it's going to be, Chris, what are you doing? You're letting the professor here off the leash, or you're out in the tall grass out there.
Chris,
You know?
we are in the off
So-
leash section of the dog park right now, and things are going nuts.
Yes.
Yeah.
So Jesse, go ahead and set the stage for everybody. What are we doing today?
Okay, so this is one of our theme of minerals, the geology of particular minerals and how they're useful. What's interesting about them is you stop laughing as I'm introducing this, Chris.
I'm looking at your first image, Jesse. Like,
Yeah, so let me talk about that. We do have images that go along with these. They'll be on the app, our Camp Geo app. First link in your show notes. We'll have these images integrated with this audio content here. And some of the images, Chris, garnet's amazing. You and I've collected. We've been to some spectacular garnet locations. Many of the types that we're going to talk about, we have amazing garnets, and you have some spectacular ones. I have some spectacular ones. Garnet's just an incredible mineral. We're going to talk about how cool it is and scientifically how useful. That's the point of this thing. It's an incredibly useful. I hate to say this, but garnet is likely more scientifically useful than zircon, which pains me to say, but
Ooh,
it probably
I love
is.
it. Tell me more. All right, so
Chris,
I agree
let me real quick.
100%.
Let me just interrupt real quick. This episode is part of the theme. It's on the app with the images, the Camp Geo app. You can go there and you'll find this episode as part of our Geology of Minerals series. But that's what we're talking about. We're going to zoom in on particular minerals, and this is the second one. So sorry.
This is episode 2 of our little series. We don't know how many we're going to have of minerals.
Probably
right?
a bunch.
We're taking a deep
And
dive.
where I'm going to keep
Oh my
typing,
gosh.
tippity typing away.
You're going to high step type. You're
right.
a high stepper. Yeah, Jesse, I mean, okay, I'm ripping on you, but you know I love garnets because, I mean, my countertops, they are garnet studded. You were just at my house recently and you remarked on them. They're beautiful.
They're
you know,
beautiful.
and
Your countertop has surprisingly, so garnet, we'll talk about this, it often occurs as this round looking mineral. It's very hard to deform garnet, but you have like lenses of garnet, and I've rarely seen lenses of
Almost
garnet
Agen,
in a rock. It's really cool in your countertops.
Thank you. I love it. And so I'm on board. Okay. But I have my work cut out for me. I think I'm up to the task though. So we're doing, Jesse, you did a horrible job of setting this up, but basically we are doing all things garnet related, but we do want to, Jesse, and I'm putting this right at the front of your brain. We got to keep this at a level that is, why is this important? Because that's what Planet Geo is all about. And also, though, we want to scratch an itch, though, too, for, okay, well, let's get into some of the weeds, Jesse. Some is the operative word on some just cool aspects of this group of minerals known as garnet. And you know what, Jesse? Can we start with that a second? When we say that we have a group of minerals, we're talking about things like the amphiboles, the pyroxenes, the micas, garnets. What do we mean specifically with garnets?
This is a really, really good and important point. This is like a universally important point. When we talk about the garnet group minerals, it means that we have a shared structure where the elements that make up that chemical structure can change without changing the structure. So, Chris, I kind of think of it like you're building a steel building. You see the steel frame in place. That's the structure. You know, you've got the engineers lay out the grid spacing and, you know, which beams go where, how many I-beams where, etc. We're just replacing some of the beams with aluminum instead of steel or something. And it makes a different end member composition. So in garnet, we have many, many, many different what are called end members, which are the chemically pure form, which has the same structure. It just has, let's say, all magnesium on one site, as opposed to some magnesium and some iron, or, you know, the pure iron end member or the pure chrome end member. And so there are these chemical end members, and really what happens is we end up with a mix of them. Most natural garnets are not the pure end member form. They're a hodgepodge.
Can I interject a second, Jesse? Because I think that maybe something that many of our listeners might be familiar with that they can tie into would be plagioclase. When you talk about end members of this, calcium-rich plagioclase versus sodium-rich plagioclase. They're both feldspars, but they have this continuum from calcium-rich to sodium rich, and they have different properties then. They have different colors. And
yeah, that's a good point.
Like the calcium rich plagioclase are beautiful, especially like in countertops. They often will iridesce and change purplish and bluish and greenish and in different lights, right? And so maybe that's something that a lot of people can tie into easier than maybe garnet in terms of end member continuums.
Absolutely. I think that's a really good way to put it, Chris. And the difference there is that I'm going to turn to image number 1 in our stack here, which is just an example because garnet is used. It's a funny image. It comes from a museum collection where we have basically the color spectrum of garnet. And this is usually, the garnet can be called the rainbow gemstone because garnet's a gemstone. It's actually my birthstone, but it has a ton of different color combinations. In each of those color combinations is a slightly different chemistry. And there's some end member ones in here. On this image, we go from the brown grossular to the green grossular. And they're different chemical constituent parts, but it's all kind of grossular end member. And so there are all sorts of different things that can change the color of the minerals. And one of them is the composition, the chemical makeup of this thing. But just one last point, and then we can maybe move on. But you use the plagioclase description of calcium to sodium. That's like a one-dimensional. You have 2 end members, so there's like one line between them. You can either be 100% calcium or 100% sodium or something in between those. Garnet, imagine that in like 7 dimensions, where there's all sorts of different places you can go because garnet's a really complicated mineral formula, and you can plug different elements into different positions, different sites. You have just a bunch of different knobs to turn. And so there's many, many, many different combinations of garnet composition. It gets so complicated so quickly, and it's definitely in the weeds. We don't really need to worry about that for the purposes of this
Here's
episode.
what I want to know then about the weeds. What mineral group is garnet a part of?
Oh, it's called a nesosilicate. It's the group. I mean,
All
it's
right,
a
hold
silicate.
on
Sorry,
now. Hold on.
silicate. I'll be back out of that. Did you mean silicate?
Exactly. That's what I meant. Yes, exactly. Okay, so you got 10 seconds to qualify that. Go.
Okay. Garnet is a silicate based on silica oxygen tetrahedrons for sure. However, it's pretty complicated because the silica tetrahedrons are not touching each other. And that means that there's a bunch of different cations between the silicate tetrahedrons. And I'll take a little bit more than 10 seconds, Chris, and just point people to our Camp Geo app thing where we talk about, first chapter, we talk about minerals and we show silicate tetrahedrons. We talk about the different types of silicate minerals. You can have a single chain, double chain framework. This is a nesosilicate where there's a lot of cations, a lot of other cations in between the silica tetrahedrons, which means that we can fit a bunch of different cations in there: sodium, potassium, iron, aluminum. We can fit them in there.
And so for everybody that is not really familiar with that part of chemistry, cations is a reference to metals, and you alluded to them. Positively charged metals like calcium and magnesium, and iron can be one. Sodium, we call those cations. They are what I always say, and this is corny and stupid, but I always say it's positive,
Chris,
because it's a cat.
I use this every year in my class, and I usually say it, and then I take a deep pause and look at the room, and and then I'll every once in a while, after like a couple seconds, they'll start grinning at me and laughing at me, and then I'll get a deep groan or two as I reiterate, guys, I expect a laugh when I say this.
Oh yeah. Here's what I say, Jesse. First of all, do you do the pause though? Do you do the
No.
You don't do the pause?
Do the pause. No, not yet.
Okay, I'm right now. I'm like doing my cat pause to Jesse.
Chris is pouncing on the computer.
I do. When I do this, Jesse, you have to do the pause.
Okay, I'll try it next year. I'll try it next year.
Positive.
It would be good with the Nittany Lions at Penn State. I could, do the mountain lion.
You need to hit the green button, and it goes rawr, like that at like the football games.
Exactly. Oh,
and
it's
you
the
do
most
positive.
annoying thing. Yeah.
Yeah. Yes.
That's good. Oh, I'll bring that in next year.
If they don't laugh, here's what I always say. Whenever I say something clever, they don't think it's that clever. I always call them out on it and say, like, guys, I did not get the proper level of appreciation on that. Can we revisit this, please? Like, and say it again.
Yeah, that's right. I agree. I tend to belabor it. I tend to stand there and stare at the big auditorium of students, and then every once in a while I'll get a laugh or a smirk. Anyway, okay.
So, Jesse, I want to transition here to why is garnet useful? Like, it's such a prominent thing, like in industry with sandpaper and things like this, right? There are so many applications to garnet, and we actually talked about this with our Grand Canyon Visual podcast series, where garnet was instrumental in piecing together the story of the Vishnu schist. How deep did this stuff form? All of that knowledge came from chemical analysis of the garnets, because it's a garnet studded schist.
Okay. It's a great point. I'm so glad you brought that up. I'm going to make one point, and then I'm going to turn a question to you. So get ready with an answer to a question you've not heard before. But That's exactly why garnet is so scientifically useful. I'll qualify that as scientifically useful. So back up to, we said we can stuff a whole bunch of different cations in this structure. Okay, understand that. First and foremost, understand that we can fit a bunch of different cations in the garnet structure and it can still be stable. That means that garnet is stable in a ton of different geological environments because you can stuff different cations in there and you can torque the crystal structure. If it's low temperature, you can make a happy version of garnet at low temperatures with a particular chemical structure. You can do the same thing at high pressure.
Oh, hold on. Do you mean with a particular cation?
A particular, yes, a particular like recipe of garnet. You can make it stable at low pressure or high pressure or
hold on.
low temperature.
Yeah, that's exactly it. I want to double click on that because what you're saying, when you say a recipe of garnet, you were talking about temperatures and pressures. So in essence, then, we can extrapolate depth of formation based upon the chemical composition of the garnet. What's in it? Because it only fits in certain brackets.
Exactly. And actually, Chris, garnet's really complicated, but if we understand the what are called thermodynamics, how the elements interact with each other at different pressure and temperature conditions of an entire rock, we can actually do way more than just the pressure. We can understand the very, very specific pressure temperature conditions that a particular garnet formed in if we know the recipe for the rock. So that's where I kind of want to end with it. We'll come back to this, I think, and get into like how this works in a little bit more detail. But Chris, I want to turn it to you because I don't know this answer. You and I've looked at a bunch of different chemical end members of garnets, which have different colors and form different environments. What's your favorite end member of garnet? Or what's the one you like, I don't know, either like the most and what reason?
Oof, that's a really difficult question for me because my answer is intertwined with the beauty of the mineral and the story that it involves.
Okay, hold on real quick. I love that because every rock tells a story. Garnet tells incredible
I meant the
stories.
story that you and I have, like you and I getting it.
Okay, all right. So I think I might know where you're going now then. Okay, so finish this. I love the stories that these things tell.
Grossular garnet is not my aesthetically favorite mineral on the planet, but I love me some grossular because you guys almost killed me for grossular garnet.
Okay, I'm glad to hear this. All right. Grossular, Chris. What is grossular garnet and why is it not so aesthetically pleasing to you?
It's pretty, don't get me wrong, but it's just this brown. It's got a little bit of orange in it. It's kind of this orangey brown color, I guess. So it just doesn't do it for me.
Maybe let me interrupt real quick, Chris, and let me go through a couple end members quickly, and then I want you to tell the story about why grossular is your favorite. Right. So I'm going to go through just two end members and then come to grossular. So image number 2 in this episode stack is almandine. Here's a picture of almandine. This is a really, really common one. It's an end member. So a lot of the rocks you'll see that contain quote unquote almandine, they're not actually pure almandine, but almandine has iron in one site, aluminum in another site, and then silica and oxygen. So it's FeAlSiO, and then different numbers of those ions in there. But this is the kind of reddish, purplish, brownish one that you'll find in a lot of schists.
Super common.
Yeah, super common. If you pick up a schist and it's got, micas in it and you see some little tiny garnets, these kind of not quite ruby red.
I have a bone to pick with you.
Why? What bone do you need to pick with me?
Why did you use this picture? Why did you not just go out into your yard and take a picture of the Gore Mountain almandine garnet?
I know.
This is not okay.
Okay.
You have unhappy Chris right now.
Okay, all right, fine. The Gore Mountain garnet, I'll take a picture of a Gore Mountain garnet. How about you send me one with your smudgy camera from your iPhone? Send me a smudgy picture that we can put on here.
Well, I will. I got to wait. Tomorrow's supposed to be sunny. Maybe I'll get one.
Okay, yeah, do that. Because Gore Mountain garnet's huge, softball size, volleyball size garnets that are
baby's head.
I mean, huge. So almandine, Chris, that's almandine. You'll probably see something that's like dominant. If you pick up a schist, it's not pure almandine, but it's kind of in that ballpark of chemical composition. Pyrope is another one. I'm going to talk about pyrope. This is the magnesium-rich one, magnesium aluminum, silicon. And Pyrope is near and dear to my heart, Chris, because, well, okay, let me ask the question. There's a lot of magnesium in this thing. Where on earth is there a lot of magnesium, Chris?
So is this your question to me that you alluded to like 20 minutes ago or not?
No, this is a different one that I thought of. We'll come back to that one later.
I really, Jesse, I think I need to reevaluate who I associate with.
Yeah, you don't keep good friends, that's for sure.
I don't. Okay, what's your question?
This one has high magnesium, so I'm kind of asking, where do you think pyrope is more common because it has a lot of magnesium?
Upper mantle, I would say.
Perfect. Okay. The mantle has a lot of magnesium, right? A lot more than the crust. That's where a lot of the magnesium is tied up. So pyrope is a mantle one. And actually, we talked about this, Chris, when we interviewed Kevin Krajak. We were talking about, diamond exploration in the barren lands and stuff like that. There's a particular chromium-rich pyrope that we call G10 or G9 garnets that's used as a tracer for diamond-rich kimberlites. And so, I don't know, that's near and dear to my heart because I work up in diamond country. It's very pretty. Image number 3 has this beautiful, beautiful, deep, deep, deep red-purple color that is indicative of pyrope garnets, especially these chromium-rich ones are really, really purple. So they're beautiful, and that's image number 3.
Hey, question then. Pyrope, is this the same kind of garnets that is in the like Wrangell, Alaska schist?
That's a good question. I don't know. I'm not sure. You can get pyrope-rich compositions that are... Pyrope-rich means there's a lot of magnesium in the garnet because pyrope is the end member of magnesium aluminum. So I'm not sure.
I only ask it because it's that deep purple, same kind of color, and it's not almandine.
Oh, okay.
It still has the dodecahedron crystalline structure and all that, but...
Oh, Chris, that's something we forgot to mention, the dodecahedron. So garnet often looks like it's very round. It's a dodecahedron. There's 12 sides on it, and it's very round, and it's almost always round. It's very hard. We've mentioned this before. It's very hard to deform garnet. It's isotropic, so if you look at it in a thin section, you cross polars. It's going to be dark. It's going to be black. It means that it's
a physical beast.
It's a physical beast. It's a physical beast like quartz. It is a physical beast, and we'll find it in beach sands. I mean, in Michigan, Chris, you'll see this in the dark layers in the beach sand. They'll often have a really purple tint to it.
And it's super important in those Michigan beaches, like the pictured rocks formations, because it's a signature. You can tell where that sand came from based upon the garnet content.
You mean what was eroded to form the sand? Is that what?
Where was the source material for this sand based upon the garnets that are in it, which I think is just so cool.
So cool. I mean, the modern stuff is coming.
It just speaks again to the signature aspect of garnet, right? Yeah. We can determine a ton from it, not just temperatures and pressures, but it has this chemical signature. We can say this came from here.
Yeah, right. Exactly. Because there's so many different possible chemical compositions of garnet that you can kind of get really, really specific. So the specific thing, image number 4 is grossular. This is this kind of cinnamon brown color, and this is an image of some grossular. And Chris, all right, what's the story? Where were we? Why were we chasing grossular, and how did we almost kill you?
Well, first of all, this grossular is way prettier than mine.
It's true. I agree.
I love mine, and I wouldn't trade mine for this. But it was a skarn deposit. And, we talked about skarns in some previous episodes, and we interviewed, geologists that's what they do. They spend their life dealing with skarns and grossulars and so on. We were after this bad. And when we finally found this skarn, it was a big pit. And there was this kind of shelf where this rock extended over the pit. And for some reason, I just got excited about the garnets that were down in the pit. So I jumped down in the pit, and you and Andrew DeWitt, our good friend, jump on top of the rock that is overlooking the pit, and it collapses, and it almost crushed me.
It's not really a laughing matter. It's funny looking back, but it was like this big rock overhanging this pit where people had been digging under. And so a skarn deposit, the grossular often forms in skarn deposits where you take a limestone or a limey shale kind of composition, and then you metamorphose the heck out of it. Grossular is a calcium aluminum end member, and so calcite in limestone has a ton of calcium in it, so you can make garnet out of this composition if you push a bunch of fluids into it. And so this is a really common thing in skarns, which are contact metamorphic aureole deposits, basically. And we were looking at one of these, and I that was kind of the thing where like it happened. We look at each other and we're like, oh, that could have been real bad. Like, we got to be more careful after this. You know what I mean?
Joyce is not going to be happy listening to this episode. She's going to be like, wait a minute, what?
That's
what
true.
Happened? I never heard about this.
Joyce, it's okay. It's okay. Your son is still alive and healthy. He didn't get killed by some former students in, upstate New York.
But the story behind that, and like, we had to work hard for this stuff, and like physical labor and also mentally just trying to locate this.
Oh man,
that was really hard to find.
Was that the one where we were knocking on doors and we rocked up to the guy who said if you had the whole nine, you go up past the whole 9 yards.
The land. He said height the land.
Height the land, and you go past the whole 9 yards and hang a left. And we were like, what? And then we heighted the land, and we're like, hey, we heighted the land. And we're like, where's the whole 9 yards?
He also said you got to go past the 500s. And okay, so let me translate this whole thing. Height the land means you got to go over a hill.
Yeah.
The whole 9 yards is you drive by a yard that is a massive junkyard.
It was very clear that was the whole 9 yards.
Yeah, that's the whole 9 yards.
I remember
he's like, you'll know it when you see it.
We were driving and we jumped in the truck and we're like, what the heck was that guy talking about? And then we got on top of a hill. We're like, okay, is this height the land? Yeah, probably. And then we go past this house with a lot of stuff in the yard. And we're like, oh, that's definitely the whole 9 yards.
Yeah. And then we went past these massive, was it a transformer station? I think it must have been, right? And that was the 500s. Okay. I still don't really understand that, but I think
But you know what?
Some voltage or wattage, whatever.
You know what? Once we got over the interpretation of the directions were incredibly accurate. He was like, oh yeah, height the land, pass the whole 9 yards, hang a left at the 500s. Okay. Yeah, man, whatever.
We owe that guy a debt.
Absolutely. So yes,
we found gosh, did he provide us with hours of laughter?
I would say decades, Chris, because we're still laughing about it.
But the directions were spot on, but we had to it was a riddle.
Oh my goodness, so fun. But you know what? This speaks to the interesting part about grossular and skarn deposits is they're really localized. An almandine schist is going to be over an entire region. Where I live in I used to live in Wissahickon schist country. It's like all of eastern Pennsylvania down to Baltimore, all the way up the East Coast, down to DC. You'll be in the Wissahickon where you can find little garnet studded schists around. This grossular stuff only occurs in really localized areas around igneous intrusions, basically. So anyway, that's grossular. Do you think, Chris, we've covered the end members? Is that enough end member discussion, or?
I think so. It's just enough weedy. Yeah, I think so. So I want to transition then into garnet. It loves certain elements. We talked about this in other episodes where we have these siderophiles, these iron-loving minerals or elements, that attach to iron. And when Earth was differentiating, they just went with it, right? And iron, super dense, sank right to the core. So these rare earth elements went with it. So what is it with garnet and this same kind of affinity?
So garnet, and this applies to most compositions of garnets, most of the end member compositions. We have a group of minerals that you've probably heard of, and if you haven't, you should listen to our podcast more, is the rare earth elements.
Yes, you should. Can we double click on that?
Just reiterate that point. The rare earth elements, we will hear about these as critical minerals now, or critical elements. Neodymium is one. Your neodymium magnets that you have in your phone or your car or whatever have a rare earth element in them. But these are a group of minerals that we as geochemists love. And we love them because they tell us a lot. They're trace elements, so they occur at parts per million level concentrations in most rocks. They're really good chemical tracer of processes, basically. And the reason they're a chemical tracer of processes is because certain minerals love the rare earth elements. And garnet is one of them. Garnet just soaks up all of the rare earth elements. And so I'm going to turn to image number 5, Chris, and I'll try and describe this for those of you that are on the podcast, but you can also go to the app and look at this image. We have a group of rare earth elements. We refer to them as lights, mediums, or heavies, and there's about 12 or 13 of them, and we list them from light to heavy, left to right. Light being on the left, heavy on the right. Garnet in particular loves the heavies. So garnet will soak up the heavies. It doesn't really love the lights. If you look at the pattern of rare earth elements in garnet, it'll start low on the left and it'll kind of be like an upside down ladle, Chris, is kind of the way I describe it. It kind of goes up and then curves over, but it kind of goes up steeply to the right and then kind of levels off. Big Dipper, is the Big Dipper like an upside down Big Dipper? Is that a fair kind of shape to apply to this curve here?
This is more like a spoon.
A spoon. Okay, fair enough. Yeah. Hold a spoon upside down and point it up, and it kind of goes up and to the right and then curves and levels off. So that's what garnet does. It takes in the heavies. It doesn't really love the lights. What this means, and this gets a little weedy, Chris, so help me out here. What this means is there are other minerals growing while garnet's growing. Those minerals will not have the heavy rare earth elements in them. So zircon's another mineral that takes in these rare earth elements. If we look at zircon, and zircon grows without garnet, it'll have a lot of the heavy rare earth elements into it. It'll not have very many of the lights. It'll be kind of a similar pattern to garnet. However, if garnet and zircon are growing at the same time, the garnet is soaking up all the heavy rare earth elements, so the zircon will not have very many rare earth elements in it. So what we can do, and we do this in my lab all the time, is we measure zircon, metamorphically grown zircon, and we measure the age of the zircon, and we measure the composition of the zircon, the rare earth elements in the zircon. And we can tell, did that zircon grow in the presence of garnet, or did it not grow in the presence of garnet?
Based on the presence or absence of rare earth elements.
Exactly, specifically of the heavy rare earth elements. So if zircon, it has that kind of upside down spoon shape, it'll be like, okay, it grew without garnet around. If it goes up a little bit and then flatlines and the rare earth elements are low in that zircon, it means that there was also garnet present. And because you talked about garnet being such a pressure sensitive mineral, that rock had to be metamorphosed deep if there was garnet present.
So for the sake of clarity then,
Yeah.
What's the takeaway from this image, or maybe just the point in general? Like what's the 15-second spot on this?
Okay, the 15-second spot is that we're very interested in garnet, whether garnet's present or not, because garnet's a very pressure-sensitive mineral. Deeper, more garnet. Shallower, less garnet.
Let's double click on that then. Why is that important that it's a pressure-sensitive mineral?
If we're looking at metamorphic rocks, Chris, at the surface, and we want to know how deep did these get dragged down a subduction zone system? Was there a subduction zone system here back in the past? We would want to know, did these rocks experience high pressure or not in their history? Did they get dragged down to 30 kilometers deep or not? If we're looking at a magma, granite at the surface, we might say, okay, where did the magma for that granite get formed? Did it come from super deep, the base of an arc, or did it come from 5 kilometers below our feet, relatively shallow? And we can look at the rare earth elements in the magma and say, was there garnet present when this magma formed or not? Because garnet soaks up these rare earth elements.
Okay, so if there is garnet present, does that mean it formed deep or shallow?
Deep. If there's a garnet, quote unquote, garnet signature, which means that the mineral of the melt has less heavy rare earth elements in it, it means that there was garnet present. It means that melting happened deep, or that zircon formed deep.
Okay, and how accurate are we able to get with our bracket? Like we're going to say this formed at 6 to 8 miles deep. What's our degree of accuracy on that?
It varies a lot. Usually it's kind of a little bit of an on-off switch. It's like, was it below 15 kilometers or above 15 kilometers? Something like that. You know, garnet's kind of a mineral that's present or absent, and it gets present below, let's say, 15 kilometers or something, and it's absent above that. But in some instances, Chris, and especially in the metamorphic petrology community, if you have the rock itself, there's a PhD student who graduated, worked with a colleague of mine, Andy Smye, who did exactly this. If you have the rock itself, you have the zircons in the rock, you can do a lot better than that. So for instance, this student took a rock that came out of the Basin and Range area in the Southwest United States, measured the zircons. There's metamorphic zircons in there. And all of the zircons that formed older than 40 million years ago had a garnet signature, a garnet present signature, which means they were formed deep. After 40 million years ago, all the zircons that grew did not have a garnet signature. And the rocks themselves no longer have garnet in them. So the inference there is that this rock used to have garnet and now it doesn't. So we're kind of seeing like a signature of ghost garnet that used to be there but is not anymore. And so that's really powerful because you can say, oh, that crust used to be thick. This used to be at the base of really thick crust. Now it's in the basin range, which is thin. It has thinned over time. Like the crust has extended and thinned over time. So it's
I wonder,
really powerful.
can you see this as a continuum then along a subduction zone, an ancient subduction zone, let's say?
It gets a little bit complicated. I mean, it always gets more complicated. You're sick of me saying that, but yes, you can in time. Like you can see melts formed with garnet present and garnet absent, or going garnet absent to garnet present. And there are at the base of volcanic arcs in the southern Sierra Nevadas, in India, what's called the Costan Arc Batholith, there are arc blocks of a volcanic arc that have been tilted on edge, where you get down 30, 40 kilometers deep in the arc roots. And there are pure garnet rocks, what they call garnetites, which are magmatic garnet rocks that are formed at the base of an arc because the garnet's stable and super dense. And so it just forms in a magma chamber and gets accumulated down there. And so, in a super thick arc, you will form garnet at the base of that. And this is just an indicator. So we can look at, we're often interested in garnet present, garnet absent because it's a pressure thing. So that's a much longer answer than 10 seconds, Chris. And I'm
no, it's
sorry
way
about
longer.
that.
I didn't do a good job there. But basically, I think like it all comes back to this recipe of temperatures, pressures, and also other elements or minerals that were present or not present.
That's exactly right.
And so we're really able to hone in then on the history of that piece of whatever you call it. I don't know, what do we call this? A crust or?
Yeah, piece of the crust, whatever rock we're looking at. And the amazing part about garnet, Chris, is we can look at igneous rocks, we can look at metamorphic rocks, we can look at skarn deposits, and they all have garnet in them. And the garnet all helps us tell the story because it's in part because it's such a complicated mineral, because there's so many different end members, and because it's been studied for decades, we understand those end members really well.
I think of all of the instances, Jesse, where, you and I have been sometimes together, sometimes not. You talk about the Tetons and, the Grand Canyon and out east and where we were in, I don't know where we were then, upstate Maine, I think, when we were looking at the grossulators. I mean, piecing together the geologic story of the Tetons and these geographic areas, you couldn't do it without garnet.
Absolutely not.
Or it would be a very different process, I think, at the very least, which is just, I don't know. So that really helps.
That's a really good point, Chris, and I think it helps paint this visual of how common garnet is in so many different settings that are so different, both in time and in chemistry and tectonic setting. It's a super powerful mineral because of that. So let me, Chris, if you'll allow me a little bit more weeds.
All right. Well, because we're going to transition here into garnets. And, oh my gosh, I shudder to think of this.
Say it. Say the word I love, Chris. Say it.
Garnets and geochronology.
Geochronology.
Oh my gosh.
I love it. I love it.
We've got to keep it tight, though.
Okay, we'll keep it tight. Chris, I was trying to think about this. I know you do a rubidium strontium isochron exercise in your class, right?
I do.
How much have we talked about isochrons on the podcast? I'm not sure we've done
No, I don't think we have.
Okay.
Actually.
Well, this is image number 6
here. You're going to try?
I'm going to try.
This is kind of tough.
This is tough to do without an image. But image number 6.
I don't think I could do this, Jesse.
Okay, I spent a while pondering this, and the image is a really basic isochron image. I'm not sure how well it does. It's a little GIF, and it shows how an isochron works. I'll try and do this, Chris. Give me 20 seconds to kind of describe the plot, but it's complicated. This is something, Chris, as a grad student, I'm embarrassed to say this, but this is something that I had to have several different takes to understand. So I would go into my supervisor, Tom Chaco, saint of a human being. I'd go into his office and be like, Tom, I don't understand how an isochron works. Can you explain it to me?
Can I interject here? I think I know why. Because like understanding an isochron, and you can't do geochronology if you don't understand isochrons, right? Is a multi-step process. And anytime you're dealing with, you have to do this, and this, and that tells you this information. We get lost after a step. I have found this to be true with my students. Anything that involves more than a step is going to take, like that. You got to tease this out. It takes time.
And I think it's because in some part, I agree completely with you, Chris. People get lost at different steps for different reasons. And so as a teacher, As soon as you go 3 steps deep, you're presented with a range of options for why students aren't getting there.
Yeah.
And each one is different
So
and
many
unique,
variables.
right? And so for me, I had to go back over the course of 6 months. I had to go back into my PhD supervisor's office 4 times to really understand an isochron. And he had to bring out the exact same textbook, show me the exact same image, which is image number 6, what I'm showing you here, and explain, here's how an isochron works. But basically what we're doing is we're saying there is radioactive decay going on. Let's say, in this case, lutetium decays to hafnium. So 176 lutetium decays to 176 hafnium. The numbers and the names don't really matter for this purpose. Some rocks will have lots of lutetium, and some rocks will have not lots of lutetium. The rocks that have lots of lutetium will, over time, produce lots of hafnium, the daughter isotope or the product isotope, faster because there's more atoms decaying. What we do in isochron space, it's just a graphical representation of radioactive decay, and it graphically shows how we get an age. Rocks with a lot of lutetium will plot on the right of this plot. Rocks or minerals with less will plot on the left. And so we can take what geochronologists do with garnet is they'll take garnet, they'll separate out garnet from the rock. They'll crush it up and hand pick garnets out. They'll dissolve the garnets. They'll dissolve the whole rock. And then they'll also crush up the matrix, which is what's left behind after you separated out the garnets. So you kind of have garnets, rock, and rock minus garnets. And you dissolve all of those.
The gist of it is that all of these different components are going to have the lutetium in it and the hafnium in it.
They're just going to have different amounts of each.
Exactly. And that's the point. That's the important thing, is that each component is going to have a different amount of it. And when you plot these out, you get the slope of a line.
Exactly. And so, Chris, let's think through this real quick. And this is how I finally became a geochronologist who understood isochrons back in my grad student days, is you have to kind of think, all right, you have to play it forward, a hypothetical. Like, okay, let's say we just formed a rock today. We created garnets, we created the rock, and we created the minerals in the rock that were not garnet. Garnet, because it loves, lutetium is a heavy rare earth element. We talked about already how garnet loves these heavy rare earth elements. So garnet's going to have a screaming high amount of lutetium in it. It's going to have a little bit of hafnium. So it's going to plot way to the right when we say the lutetium-hafnium ratio. On this x-axis, it's lutetium over hafnium, but garnet's going to be way to the right. The rock itself is going to have a medium amount of both, so it's going to be kind of somewhere in the middle. In the matrix, the rock minus the garnet, so it's going to be to the left of the entire rock because we've removed the garnet part of that, the part that has a lot of lutetium. The rock is left with very little lutetium, or the matrix that's left behind. So, okay, today we form a rock. Great. They're going to spread out on the x-axis. However, they're all going to have the same amount of this product or daughter isotope, 176 hafnium, because they all formed today. Now, what happens if we play this clock forward? If we skip forward 100 million years, lutetium will have decayed to hafnium. 176 lutetium decays to 176 hafnium, which means the garnet that has a lot of lutetium will have less lutetium. It'll move kind of to the left on the diagram, but it'll also move up because as lutetium decays, it produces hafnium. So it'll kind of move up and to the left. And because it had a lot of lutetium, it'll move up and to the left very quickly. If we think about the matrix part, there's not much lutetium in there, so not much is decaying. It's going to stay broadly in the same part of this plot over 100 million years, whereas the garnet kind of moves up and to the left. And if we do that over 500 million years, that'll just be more extreme, that movement. The garnet will continue to move up and to the left. And so what ends up happening is if we analyze a schist that's 500 million years old, we analyze the garnets, we analyze the rock itself, and we analyze the matrix, the rock minus the garnets. Those will plot on a line, and the slope of that line is equal to time. More time is a steeper slope because the garnets will continue to lose lutetium and increase in hafnium. That is radioactive decay, and it's proportional to time. So that's broadly how an isochron works. This is really hard to get across,
You
Chris.
Lost everybody.
Okay, Joyce fell asleep a long time ago in this episode.
A long time ago. Can I just give maybe a minute crack at this, maybe simplifying this? And if I'm oversimplifying, let me know, Jesse. But, I wrote a whole lab dealing with this very thing that you're talking about, that you're describing right here. So you're trying to normalize the data, right? So we are comparing on the y-axis of a graph 176 hafnium to 177 hafnium. And my question is, as a mineral grows, is it going to differentiate between the 176 and 177 hafnium? And the answer is no, because they're so similar in size and shape, and like it's a brick that fits in the wall. It fits. So it doesn't differentiate between them. Now, the difference is that 176 hafnium is a radioactive isotope. 177 is a stable daughter isotope. In other words, it doesn't get there by decay. So what we're after is the ratio, the initial ratio of 176 to 177 hafnium. And if we can get your slope of a line that you plotted on this graph, if we can get to the y-intercept, that tells us time zero. In other words, that gives us the initial ratio of 176 to 177. And then if we compare that to what we actually observe in the rock, we know what it had originally, we know what it has now, then we can tell you how old is this rock.
Exactly, Chris. And this brings up, I love that you brought up this point, because this isochron method is beautiful because it not only gives us time, which is the slope, but it gives us, exactly as you said, the initial composition of the daughter isotope or the product isotope.
Isn't that crazy? Isn't that crazy? We need to double click on that, Jesse, that we are walking it back. Here's what the initial mineral had in it, right? And here we are looking at this, 2.7 billion years later, and we're able to tell, here's what it had. And people are like, well, how can you possibly do that? Well, okay, we can use things and test this same process with elements that have half-lives that we can measure in days or years instead of millions of years. It's such a beautiful thing. This is crazy.
It's just such a very, very elegant graphical representation of the really complicated equations that are the basis of geochronology, but you can see them all right there with the isochron thing. So it's a beautiful exercise. And it rules out, like, one thing, Chris, a lot of like people who disagree with the fundamentals of geochronology. You don't know the initial isotope ratio. We do, or at least we can do a quality assurance check using that.
And that's the thing, Jesse, is that if you can't do that, then you really can't do geochronology in this way.
That's right.
But the thing is that we can. And this is, Jesse, I would say, I don't know, I should keep a list, right? What are the top 20 misconceptions that I come across in geoscience? This is top 5.
Oh, really? Okay. The initial
absolutely.
daughter or product
oh my gosh,
ratio. Interesting. Yeah.
Geochronology is BS. It's just guesswork. And when we get data points we don't like, we just toss them out. And no, this is not how this process. This is actually a beautiful process.
Oh, it's so elegant.
I am in love with it. It is an elegant, beautiful process, and it is 100% testable and reproducible, and I love it.
So on that note, Chris, let me do 2 other points about why garnet's great for this. First of all is that in order to do an isochron method really well, you want to really know the slope of this line really precisely. And so what do you need to know the slope of this line really precisely? You need a huge range in lutetium hafnium preference. And the good news about garnet is garnet loves lutetium and it really doesn't like hafnium. So it plots really far to the right. It plots way, 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 way to the right compared to the rock. So it gives us like a really good hinge point. If you imagine this like a lever, this is a really, really powerful lever because it's way out there in space. It's a really, really heavy lever. Like this gives us a really big weight on this line. And also the other beautiful thing about garnet is that we can use this same isochron method using 2 different elements. Samarium decays to neodymium, and garnet does the exact same thing in that space. It has a high samarium neodymium ratio, so we can use a completely different isotope system with a different half-life and different chemical affinities, and we can compare the lutetium hafnium age to the samarium neodymium age. And usually they agree, and if they don't agree, that's something really interesting about the garnet. And so people have done this where they take a garnet, there's zones in garnet, like growth zones, and you can like take a little micro mill and mill out the different growth zones, and they get different samarium neodymium ages from different growth zones. It tells you how long this garnet took to grow, and in some cases it's tens and tens of millions of years for one garnet to grow. It's a really incredible thing, and people are experimenting with uranium lead geochronology in garnet, and certain garnets it works really well for. So there's a bunch of different isotope systems we can throw at garnet, again, because of this chemical variability that garnet has that is inherent to the garnet structure, we can throw the book at it from these geochronological techniques. So anyway, that's enough of the weeds on geochronology.
It's exciting.
Maybe it's cool.
And I think, Jesse, I think this is a good place to end. What do you think?
Will you allow me one more tangent, Chris, on garnet, on the scientific utility of garnet?
Okay. Man, Jesse, you're killing me here.
We're having so much fun in the off-leash section of the dog park, Chris. Like, we don't want to go home.
And I'm so excited about this whole isochron thing and what you can learn from garnets. And it's not just garnets, but garnets are really, really important with this process. All right. Yes, I'll give the leeway on
okay,
this.
one little thing. We're going to talk about
one little thing. Yep.
This goes back a long time. This is like an early development in sort of petrology techniques and what's called iron magnesium exchange thermometry. How this works is garnet has iron and magnesium in it. We've talked about almandine. We've talked about pyrope. There's iron and magnesium in garnet. There's also iron and magnesium in a bunch of different minerals, biotite being a relevant one here. If garnet and biotite are sitting next to each other, there will be exchange. Chris, we've used the analogy of like brick walls. We're making walls of different bricks. So some of them, are yellow bricks and some of them are red bricks. And iron and magnesium are the different colored bricks. And they're in the walls. Let's say we've got two walls next to each other. We're exchanging the bricks back and forth. That's diffusion. That elements are jumping back and forth at different conditions. Basically, these two elements, iron and magnesium, these ions have a similar volume, but they substitute with each other based on temperature. So, the temperature, they distort the lattice of both these minerals. And so each mineral will have a different preference for iron and magnesium depending upon the temperature. So what this means is people who've made experiments that calibrate this thing, and there are people who did in the 70s and 80s who kind of grew garnet and biotite next to each other at different temperatures, measured the iron-magnesium ratios. You get a really consistent pattern out of that. Basically, with higher temperature, more magnesium goes into garnet than biotite.
So basically what that means, Jesse, is that you're going to be building two different brick walls. One using black bricks and one using yellow bricks, right? The black bricks, let's say, are magnesium. And so that's what's going to go into, at higher temperatures anyway, that's what's going to go into building the garnet. Whereas then the biotite by default is going to use more iron. And so you're building two different brick walls here.
Exactly. We're building brick walls, and as the temperature changes, the stability of those brick walls changes. And for various reasons to do with the crystal structure, garnet likes more magnesium at higher temperature than biotite likes magnesium. So the image number 7 there is just showing that there's like iron and magnesium atoms. As we go up in temperature, there's a garnet thing on the left and there's a biotite thing in the bottom right. And the garnet will take in more magnesium faster than the biotite will. At the end of that, at higher temperature, there's a lot more magnesiums in the garnet. And it's beautiful because it's not very pressure sensitive. Magnesium and iron have similar volumes, so they're not very pressure sensitive. Makes it a great thermometer. So across a range of pressures, this is a great temperature measurement. So we can measure the magnesium-iron ratio in biotite and garnet right next to each other, and we can get a temperature at which those things grew. This part's a little complicated, but it's really simple compared to what the modern version of this is, which is to do this on an entire rock scale where people measure the composition of a metamorphic rock. Let's take the garnet schist that we saw in Gore Mountain, where we have amphiboles and plagioclase and garnet. Say, all right, take the chemical composition of that whole rock. We now know enough about the thermodynamics of metamorphism where there are computer programs that calculate at all pressure and temperature conditions what minerals will be in the rocks. Not only what minerals will be in the rock, but what percent of each mineral will be in the rock, and also what composition of garnet will be in that rock. If somebody gives, not me, but my colleague Andy Smythe, metamorphic petrologist, gives them a composition of a schist and says there's this much aluminum, this much sodium, this much potassium, this much silica in that rock, he can create a map in pressure, temperature, space that tells you what that rock will look like at any pressure and temperature, what the minerals will be, how much of each mineral will be there, and what the composition of the garnet will be, which is an incredibly powerful tool to turn that on its head and look back at the rock record and say, oh, my garnet has this magnesium iron ratio or this manganese content. And so that means that this is the history of the rock because of the thermodynamics, or at least this is one possible thing. So this is just a relatively simple example of modern metamorphic petrology, which is really complicated, but this is a fairly well understood process now because there's been
exactly. And if you use this method right here, the iron magnesium exchange thermometry, it's another tool. We talked earlier about how we can look at garnets and infer temperatures and pressures, these brackets, right? And now we're looking at the biotite to garnet ratio of iron and magnesium, and we can infer temperature. So in other words, like we have a big toolbox that we're using. We're not using one thing. This is really complicated stuff. Actually, this geochemistry that's being applied here, it's amazing to me the number of tools that are in the box that we use to arrive at the story. How did it get there? Where did it form?
Chris, I think that's a really nice way to put it. Our toolbox for like telling the story from a rock, we have a big toolbox to leverage into. We can tell detailed stories of rocks in a way that is really astonishing to me. Even, when we're doing this every day in the research group, like every once in a while you kind of step back and think, this is really impressive. Now, there are uncertainties. There are ways to go wrong for sure in these calculations because, the computer does not model reality very well most of the time. But it's at least a tool. It's not the solution, but it's a tool to like tell a bit more detailed story about a rock, about the garnet schist, the Vishnu schist at the base of the Grand Canyon, or the Gore Mountain garnets, or the Wissahickon schist here on the East Coast. You could tell some amazing stories out of these rocks, and garnet's really instrumental.
It's
cool.
It's impressive. Chemistry with an application, Jesse, is beautiful chemistry.
It's a fun hammer. It's fun to have a hammer and hit a nail with it. It's really boring to just look at a hammer and study it. But
That's right.
Oh man. Right. So Chris, grossular, that's your vibe?
No. It's actually no. I got cut off in my story. I think almandine, but it's complicated because it's hard to separate our human stories with just the beauty of the mineral and what that mineral can maybe tell us that's more detailed than just grossular garnets. And I don't know. Depends on the day, Jesse. It depends on the day.
Depends if you're feeling beauty or if you're feeling a bit nostalgic or what you're feeling. Yeah. Okay.
Absolutely.
That's fair enough.
You know what, Jesse? Depends on which one I'm looking at.
Okay. Hey, I like that. That's a good answer, Christopher. That's a very good answer. Do you have a really good garnet in your showcases in your classroom, in the bookshelves?
Well, I have Gore Mountain in there.
Okay. Yeah. All right.
Yeah. And I have Wrangell, Alaska, and I've got the garnet schist, and some of that stuff is spectacular from the Black Hills. Those almandine garnets that are in there, which are, like you said, are not like necessarily pure almandine, but
they're beautiful.
Some of them are just spectacular. Deep red, they're awesome. So yeah,
super beautiful. Yeah, garnet's a great one. I think people like garnet too. Anyway, what is that a wrap? We have to go home, Jesse. Now.
We went long in the tooth.
We have to leave the dog park. That's a bummer. Awfully share ya. All right. Well, hey, that's a wrap. There are many ways to support us. You can head over to our website, planetgeocast.com. There we've got some merch. Send us an email, planetgeocast@gmail.com. You go to our mobile app. The first link in your show notes is the Camp Geo mobile app. There you can get all sorts of content, visual podcast series, our Camp Geo introduction to the geosciences, which is there for free, also some paid content, and this episode with images is on there as well. So head there, first link in your show notes. If we didn't cover something about garnet that you want to know, send us an email, planetgeocast@gmail.com.
Cheers.